over mmcf. In the lecture note, it is what mmcf and with S and without S. Add S. Totally, did you start?
Yes.
Okay. Add S. For this homework, whether you have S or you don't have S, I just give you full point, okay? But in the exam, add S into that. It's clearer when we say standard. Okay. Question? For the field trip, number one, we need long pants, steel-toe shoes, hard hat, safety glass, and you may bring your jacket. It can be a little cold, okay? And who don't know what time to come? There are two sessions, 9 to 12, right? And 1 to 4 p.m. Okay? If we have more spots, you can stay whole day with me and Mr. Bula. You're welcome. You can stay 2 sessions and you don't get anything more, but you can stay 2 sessions. I think you're ready for quiz, but we don't have quiz today. I may wait until you're not ready and I keep the quiz. How about that? Today we will try to cover everything about hydrate. For example, Hammer-Schmidt equation, Erosional Velocity, LTX unit. And then try to go over a little bit on what's that? The separator. Before we start, any concern? Anyone want to talk about anything that's related to academic? No, nothing, right? Deadline for homework is like 1 second before midnight. Try to do it. Okay, let's start. Previously, we talked about pressure drop in a pipe. In Silva's textbook, on chapter 2, indirect heating, there's a chart show what kind of flow rate that make velocity to be 80 feet per second or something. Anyone see that? No one see that. Don't worry about it. I put in the homework, okay, for this coming homework. We talk about the pressure drop, okay, and I show that I calculate for every cases. It may not be like very clear now, and we will go over the example to make it very clear. Look at this. We have several cases. Okay, we have the firebox rating, tube size. Sometimes for the same firebox rating, we have 2 kinds of tube size. We have multiple choices. Several of them. We have to select just one. Okay. Pressure drop is also depend on the length. If it is longer, it has more pressure drop. Look at this one. 2 inch with just 68. So this one has, how many coils? Number of tube is 8. For 2 inch with 18 tube, we have more pressure drop. And that reflects in the equivalent length, right? Example 1. We have gas flow rate of 3 million cubic foot per day. Gamma, what's gamma? Specific what? Specific gravity of that natural gas, 0.7. Inlet pressure, 200. Inlet flowing pressure, 200 psi. Line pressure, is it 2000? So basically, what we did previously is about using this chart to calculate how much heat we need, right? That's step number 1. So we need to know that, hey, we have to heat from 71 to 125 first. And we know the enthalpy difference. After we know the enthalpy difference, we know the flow rate. So we know the flow rate and enthalpy difference, we can calculate or use the chart and tell how much heat required in BTU per hour. That two method, if you remember, you can use the chart or do the calculation. And this question is, inlet pressure is 2000, so on another page it's just typo. So inlet pressure 2000, we need to choke to 750. We did it already together, and before the choke we have to heat until 125, and flow across the choke is Alexander J. Kroll. Are you here? Alexander, middle name is J. Hi, Alexander J. Kroll. Flow across the choke is a constant what? H enthalpy? Yeah, correct. It's a constant enthalpy process. We did that. Next step, after we do this, we try to see, we select the pipe. To select the pipe, there are two considerations: erosional velocity and the what? Pressure drop, right? If the pipe is too small, we have too much pressure drop, and gas inside will be too fast. It's not good. So what we do is, we try to select the case that's good enough. But let's skip that for now. Let's say we do it and we know that we use 2 inch X. So in this example, we know that we use single pass coil, and we know that we use 2 inch X pipe. 2 inch X pipe come from the consideration of I think this table, where is table? There's a table to tell the pressure that the pipe can withstand. So we have to go more than 3000, right? We go over that, so we delete all that and we select the smallest one that's not too small. Not too small means too much pressure drop. But pressure drop is somewhat difficult to calculate because there are several cases. Why do you say that? If we have 1 inch, this case is 1 inch, that is 1 inch, right? If we have 2 inch, there are several cases that are 2 inches, right? Several cases, really. So we try to get a rough number first. What is the DP? Pressure drop per unit length. And for the case of a certain equivalent length, when we get the number, we don't select right away. Then we try to calculate coil area. So coil area, parameter A is really the deciding parameter. Coil area, how do I do that? U value. When we know that we don't use 1 inch, to know what is the U value we use. U value depends on the flow rate and the pipe size. If you recall, there's a chart, right? Do you recall that? There's that chart that has several lines. We take one, which is 2 inch X. The reason that we select that is, based on the pressure drop calculation, it's not much pressure drop. Okay? The pressure drop is not much. If we have more number of coil, of course, pressure drop will be more. Correct? Longer coil will have more pressure drop. But for now, we know that, hey, 2 inch X is okay. It's okay, but it doesn't mean that 2 inch X is only the answer, okay? But it's the smallest one that it worked for now. So when we know that it's 2 inch X, we get U value of 94. We got it previously already from the chart. Let me show it to you one more time. I'm sorry about going back and forth. It is this chart. See, U value 94. Okay. After we get U value 94, we calculate log mean temperature difference. Log mean temperature difference is this formula, right? To calculate log mean temperature difference, we need to know water bath temperature. And water bath temperature should not exceed what? Stephen Lee. What is the water bath temperature recommendation? Guess one. Yeah, how much should be water bath temperature? It doesn't boil. It doesn't boil. I think it should be less than 190 or something. Okay, the number is here. I cannot find it now, but 190 may be fine. If we want to go hotter, we have to add glycol. Okay, but the typical value that people use silver citrate is 180. Okay, so when we know the temperature bar, then we can calculate T sub m, log mean temperature difference. From T sub m, we have U value. Next step, I will do this one. Q equal to U A T sub m. Jordan E light. How do I get Q value, Jordan?
Well, you get UO from the chart.
We already have it, right?
You have UO.
We have it already. That Q is BTU per hour that we previously calculated when we use this chart. We already have it. Okay? And that Q value is 3000 BTU per hour. The value that we don't know is A. Right? No, that's A. We know Tm, we know U, we know Q, then we can calculate A. So when we calculate A is the total coil area. After I calculate A value with the right unit, let's say A equal to 40 square feet, then I am ready to open the chart to find out which model to select. And done. You like it? Let's see example. Okay, over here I get my inlet temperature, outlet temperature. I calculate T sub m. Question, yes.
So you have UO is
94. 300,000 is Q. 300,000 is BTU per hour. BTU per hour come from the chart that have the dash line, the zero line, and we go like this. Okay? And the difference in the enthalpy with the flow rate, we know that it's 300,000. Or you can do calculation. That is capital Q, BTU per hour. With BTU per hour, and we know Q equal to A U T sub m. We know T sub m, we know, we know T sub m, we know U, then we calculate A. Yes, question.
What area does A represent?
Area. What is that area? That area that we get is the area in this chart. It is coil area. Okay, it is surface area of this coil. You see that?
All of the coils?
Around all of the coil, yes. If we have more coil, we have more area that it contact to water. With more area that it contact to water, we can have more heat transfer even though temperature difference is the same. Think about this. T sub m is the temperature difference, right? But if we have more area, we can have more BTU per hour because there is more area for heat to transfer. So it's kind of quicker. Good? It's kind of quicker. So that's what it is. Look at this. I get T sub m, then I can calculate coil area. A equal to Q over U and T sub m, and I get about 40. Then I look at the data sheet. Hey, even though this chart, table 5, standard indirect heater with steel pipe coil, it has several pipe, you see, there are several pipe size. It arranged such that the coil area go up. See, 21, 28, 85, or it's go down a little bit, and that, and we have more coil area. It keeps going up, right? Same as Firebox rating. Firebox rating tells us how much heat that it produces. Capital Q. Okay? Previously we know that Firebox rating that we need is 300,000, right? BTU per hour. So we should select either that. Oh, no. This one won't be enough. So we should select this or something else. Okay? But we prefer the smallest Firebox rating because it's cheap. Bigger Firebox is more expensive. So we prefer that one. And we keep our answer in mind. We don't answer it yet. And then we check coil area. Hey, coil area of, we need just 40, but this one provides 48.8. So it's more than what we need. It's good. Is it? Yes, it's good. Then we have, other than coil area, look at this. This model is 2 inch. Is that good enough for 2 inch? 2 inch will be good enough. Then we can go back to the pressure drop. Pressure drop, we look at the chart. This kind of chart. Hey, 2 inch. Do we use which one? We have X or XX. Which one are we going to do? Are we going to do X or XX? X and XS has to do more with the pressure rating. Okay. When the nominal size is 2 inch, X and XX have similar cross-section area inside. Okay. So XX means thicker wall, withstand more pressure. When I go back to this, which one do I use? Hey, XS may be just enough because shut-in well pressure is 3,000 and this one can withstand 3,400. It's more, so this is good enough, right? Make sense? Then we can check pressure drop. Hey, if I have XS, what is the pressure drop? Then I have pressure drop as how much? XS 2 inch. Oh, that model is have X or double X. So for just X, I have 2 inch X, pressure drop of something. We get P1 square minus P2 square, and we still have to do a little bit more math. And we see, hey, pressure drop is low. It's good enough. So this means 2 inches okay, right? And then last step, we check erosional velocity. Okay, let me repeat myself. Maybe I didn't do it very straightforward. Maybe I should change the slide later. Step number 1, use this chart. That's number 1. This chart is number 1. Okay. We need to know we heat to what temperature to what temperature. Okay, that's number 1. Number 2, calculate BTU per hour. After I get BTU per hour, then I can tell, hey, this one is about 300,000 BTU per hour. Then I can almost select the Firebox rating right away, right? Almost done. The only question is, so when I, with just using this, I can almost select this thing based on this thing, right? So next step is, what should I do for water bath temperature? Just select 180, a good typical value that Siva suggests. Everyone else use it. The manufacturer suggests that. With that, what is my T sub M? Okay, and look at the available pipe size. Available pipe size is 2-inch X or 2-inch double X. What is the U value? When I get U value, then I can do A equal to Q over U and T sub M. Then I can tell what is the required coil area. And if the provided coil area is small, then we're good. Then we are kind of almost done. The reason that I say almost because we have not checked the erosional velocity. Good? Question for me? No question. You understand it? Yes, yes, someone say yes. What? Tris? Yes? You understand?
Sure, just one thing, you said you can select the firebox right away, or you still gotta wait to
Almost right away, because whenever we know that it's 300,000, look at this. You don't have much choice. Look, 100,000, 250, you cannot use this too. It's not enough, right? You have this, or this, or this, or the rest. But of course, you will select the one that is lowest because it's cheapest. Okay? No more question, right? Good. I cannot clear it. Right? Oh my God, I cannot clear it. Split coil. Okay, look at this one. That's okay. Previously we talked about single pass. What about we split it? We hit it first, we choke, we hit it again. What do we do? In that case, the way we calculate Firebox rating stay the same. Stay the same. let's take a look at this. We use split coil. Coil 1 upstream, coil 2 downstream. Gas flow rate is this much. Gamma is that much. Okay, add one more zero. 2000 psi. Line pressure 750. Well shutting pressure 3000. Outlet require 120. Okay. Coil number 1, preheat. Coil number 2, downstream of the choke, upstream of the choke. So before the choke is 3000, right? Then we choke it to 750. Oh, required working pressure, I'm sorry, this is required working pressure. This is flow pressure. So before the choke, the pipe should withstand that much, 300,000 psi. After the choke, the pipe should withstand just that much. So we can actually use a thinner pipe. But we don't need to. See what suggests? They put star over there, even though X heavy is too much, but they put a comment here. Okay, X heavy is too much, but we can do with a little extra initial cost. So this may be just a matter of cost. They say usually they kept the same kind of tube all the way. Okay, tube is just the same size all the way. But we know that we can use a little less. Of course, they suggest that we can use the same tube all the way with a little extra cost, but I don't know what is a little extra cost, but I don't think it's much either. Okay, next. We know that we have choke from 2000 to 750. Is it to 750? Okay, inlet temperature 71. 71 is right at the hydrate temperature. Outlet temperature 125. Enthalpy difference is, I think this one is typo, it's not 125. Enthalpy difference is 900. And then we heat it again to, otherwise you cannot heat it again to 120. Gas flow rate still the same, 3 and 3. And you say, okay, heat required for the first case is 300,000, 240. Keep doing that. We get this much PDU per hour, and that's the answer. So this really is depend on what is the preferred temperature after everything, right? If we heat it twice, after everything, we can get temperature at the outlet to be 120. If we heat it, it just off. I think actually this is correct. What happened is, you see this number? Before the show, it is 71. We heat it to 125. Then we choke it. When we choke it, temperature drop. It dropped to 61, which is still at the higher temperature. But we want it to be hotter when it leaves. So we heat it a little bit more so that it reaches 120. Good? So it depends on what do we want after it leaves the line heater. Okay. If we want to have it at 120, we have to heat it a little more. And a little more means that much. Coil area, just add them together. BTU per hour, just add them together, and then we can select the fire tube rating. Please question? No more question? Okay. Log mean temperature difference. I have the chart. I think it's quick to use too, but you can use the calculation that with the log formula. Yes, question.
On the last slide, where did you get the T sub M from, the 1885?
T sub M. T sub M. 80 and 85. Option 2. Use the chart. I don't like it. Option 1. Option 1. Use this. Good. So we need to know what is the greatest difference, lowest difference. Greatest difference. So we need to know, okay, bath temperature, right? At the inlet, gas has a temperature of 171. After we heat it, it becomes 125. So LTM is that much. So when we have this, have that, then we can calculate it. Good? Okay, next. And here's the solution after we select everything and we tell, okay, what is the coil area and how does it split between each. One note is that they said when we select for the split case, the number of tubes will be just even number. We don't have odd number when we split. See, 8, 6, 4, 4, 4, 4, 8, 6. Every time the coil number will be even number because it has to go and come back. Okay, so this thing will be even number. Try to do a calculation that has something available. Okay, I have question. Maybe you don't have, but I have question. Who want to answer? Let me call his name. Roberto Para. Hi Roberto. How do I know how to split? Look at that. Roberto, what's your answer?
Can you repeat it?
What?
Can you repeat it?
How do I know what kind of method to split? The total number of coils can be 38. How do I know that I should use 20 and 18 or 28 and 10 or 30 and 8? Which one do I use? There are several ways to do the split, right? Yes. And every one of them, I may have 2-inch X. And I have Firebox rating of 2 million BTU per hour. But how do I split it? Roberto.
I guess the size or how much heat transfer needed.
How much heat transfer? Who know the answer? Who know the answer? Who think you know that? Oh yes. What's your answer? What's your name?
Connor,
Connor. Thank you very much, Connor.
do you look at effective length and see which will have the lowest pressure drop?
I think it's more like temperature. Yes. By the way, effective length they are all the same because total number of coils they are the same. You want? Look at this case. When the total number of coils is 38, the effective length is 500 something. How do I know how to split? Split means this. When you look at the picture, how many coils do we put over here and how many coils that I put afterward? Like this part. Before the shock, how many? And after the shock, how many? Corner, how do I know that?
Just ratio it for the added temperature, or you measure adding
I like your answer, but it's not quite precise. Let me give you the precise version. The very short answer and still correct. We use this. We use this. Typically, we heat just to reach the hydrate temperature in the first pass. So wherever it's coming in, we heat just to reach the hydrate temperature. And if I want it to go out at 120, I heat more. Okay? That's the recommendation from this. This is how they decide how to split. Okay? To do this, we have to do calculation like what they did before. I understand that this is not quite the answer. It doesn't tell why, but it tells, hey, the book said this, and I say that too. So coin number 1, coin number 2, we do the calculation on how much area do we need before and how much area do we need after. Let me ask Danny. Danny, why do we heat just to the hydrate temperature? Is that minimize the cost or something?
Yeah, so on your first pass, you don't always have to stick with the same grade of pipe on each pass of coils.
Oh, we don't need to do this star.
Right.
We can do.
That first pass may need to be double extra heavy to handle the pressure. And then you're going to go through a choke and reduce the pressure. The second set of coils in the tube, in the firebox, can be a lower pressure rated tube and they'll be cheaper. So you can split and use a lesser grade of pipe. Now, I know that chart doesn't give you that option.
Yeah, it doesn't give me that option. Or they want to give as much profit as possible.
Right.
Right.
So you can split them that way and make that, you can still have that second pass. When we get out to OTC, you'll see a split pass heater. And it's going to have some different
I think
options on there than what we saw.
I think the answer may be the cost. If I try to heat everything before I show, all those pipe has to be a thick pipe. But if I use minimum number of pipe to heat before the show, then the majority of the pipe can be a thinner one. That's it. Good. Erosional velocity. After we do everything, let's do final check. Erosional velocity. So we have to limit the maximum velocity because we don't want erosion to happen. We don't want it to be noisy and we don't want water hammer. We need some minimum velocity. Okay, we don't want liquid to accumulate in the low spot. We don't want sand or some kind of solid particle to keep accumulating. I don't know his name, but he keep talking. Sit on, you see, with his laptop over there. What's your name with the cap? Yeah. But do this. What's your name?
Carson.
What?
Carson.
No. You right next to you.
Oh,
Yeah. What? I don't catch it. Yeah. Oh, I never called you when you write the bottom. Yeah. Maybe part of it is my fault because I have his name over there, and it's like not on the list. I didn't see it. It's like added just there. Okay, I don't try to pick up on you, but every time I look at it, I see it. Okay, don't do that. Just pay attention. Okay. Clarence, right? Please help me by, when you go back home, you read the syllabus on the section of, what do we call, ethics in class, or what do we do in classroom to promote this kind of studying environment or something. Can you help me with that, sir? And if somebody else allow you to do something like that, tell me. I will walk over there and tell them to stop. How about that? Okay, pay attention. Hey, Clarence, did you listen to any of this noise or you get that? A little bit. I want you to get 100% of your tuition that you pay, okay? If you pay $100, I want you to get $100 back. Not like a little bit. Okay, we need to limit the maximum velocity, minimum velocity, to be at a certain value. The calculation is this formula. VE equal to C over square root of rho. High velocity, especially gas flow, can erode the pipe. It is noisy. So the typical value is 60 to 70. And precise value, we can calculate from this. C is a empirical constant, 300 or 400 or something is on the next page. That's the value of C. C ranges from 100 to 400 from experience. And if you want more precise version, we need to read the paper from Solomon. You should read the paper of this paper to select the precise one. Why every case is unique and all factors should be considered. Do we have elbow or we have the straight pipe? Do you have solid or something? For class purpose, we use 300 for non-corrosive, no solid. And C equal to 100 for the case that it's very corrosive, okay? And but this C value is not, universal value. Every case, if you have more elbow and you have solid, it can hit and it can erode faster. Alright. Rule of thumb. Velocity should be more than 10 to 15 feet per second. And it should be less than 60 to 80. Okay? Or V erosion, whichever is less. Even though it doesn't erode the pipe, but it may shake the pipe. When it shakes several times or several thousand times, it may fatigue. It may fail. Okay? It may have a noise. Noise may not much. You may think that is noise a big deal when we have it? So in middle of nowhere, we have noise because pipe keeps shaking or something. Is that a big deal? Yes or no? Hamed M. Masarani. Hamed. Noise. What's the impact of noise if we have this in the field?
I mean, it depends on the location of the noise.
Middle of nowhere, nobody is there.
It's fine.
It's fine? Really? I still don't like it. I don't like it because of this. Let's say you go to the tank battery. Outside it's just a cotton field, just a cotton, right? And some insect, okay, maybe a little snake, but there's no one. You hear that noise, but that prevents you to hear other noise. What if there's other leak? or something strange, you cannot hear it if it is too noisy. So I don't like it. So here's why we have that recommendation, or V erosion. And one comment about carbon dioxide before we do the calculation thing. Carbon dioxide is not quite friendly. Oh, where's my slide on carbon dioxide? CO2, oh here. In a system where we have CO2 in amount as low as 1 to 2%, velocity should be limited to less than 50 feet per second. You cannot say, hey, I have just 1% or 2%. Limit it to be less than 50, because Arnold just said that. They put it in the book. It's based on the experience. They found that it is difficult to inhibit CO2 corrosion at high velocity. Okay, so if we have CO2, keep it less than 50. Okay, if we have CO2. Okay, calculation. The calculation requires C value 100 for the case where it's very erosive, have solid particle, and if everything is clean, you may use 300. Rho is pound per cubic foot. V is foot per second. Density. Oh, it doesn't pop up?
No. I had a question. Can you repeat that? That's not a question. But can you repeat that? If C is equal to 100, C is equal to 100 for what?
For this. Yes, let me repeat it. C equal to 100 for corrosive. C equal to 300 for non-corrosive. No solid. No solid. Okay?
Gotcha, thank you.
That is C value. Density. Okay, let me call the name for those who outside the table. Alina Dupientis. Alina, where are you here? What is that role? Density of what? Oh, I meet you yesterday, yeah? Yeah, density of what? What is that role? Liquid phase? No, it's not liquid phase. What is that role? Density of what? Density of pipe. You agree? No, it's not density of pipe. It's the density of gas. Is that the density at the standard condition? No. I try to trick you every time. Okay, it's not the density at the standard condition. It's the in situ condition. If it is high pressure, it's more dense. Okay, high pressure is more dense when it is dense. So let's say it's high pressure. This value is big value, very big. So this make erosional velocity to be small. So this means when it is dense, even small velocity can erode the pipe, right? But when it's not dense, you can allow them to flow a little faster. Good? Density in the pipe, Alexander K. McCory. Hi Alexander. How do you calculate density? Oh, wrong question. In which class that you study how to do that calculation so that I don't have to repeat? Let's say I have natural gas, I know molecular weight, I want to know what is the density at 1000 psi and 100 Fahrenheit. How do I do that? Shall I skip? And you can magically do it in the exam. Good? Not good. Did you study it somewhere in the past from Texas Tech?
I'm sure.
You sure that you did? Probably. Do you still remember it?
I do not.
Oh, What about other people? Who want to skip? I want. Oh, none of you. Who sit next to you?
It's my friend Jason McEwen.
Jason, did you remember it?
No.
No. Did you study it in the past?
Yes.
Yes. Do you remember equation to do that? That has to do with this kind of thing. Do we just use PV equal to Z and nothing? Gas law? No? Did you study gas law, Jason? Okay, how do you calculate density? Someone in the past teach you that.
Should ask them.
Should ask them. Who's that person? Fluid property?
Dr. House.
He retired. Okay, I cannot ask him. We use PV equal to Z nRT. After we do work all the unit, we get two options, 2.7 or 0.093. So let's say we know the molecular weight, we can use this formula. Jason, do you know the derivation of that? Yes.
Ideal gas law.
Okay. Z is compressibility factor. T is temperature in Rankine. P is the pressure in PSIA. MW is molecular weight. So then we can calculate this rho. The derivation of this is from PV equal to nRT at the standard condition. Z equal to 1. And mole is mass divided by molecular weight. So density, we have mass over volume. I rearrange it. Then I have P multiplied by molecular weight divided by RT, that is rho. Okay? And I substitute the value. Molecular weight for air is 29. Then I have S multiplied by molecular weight. This thing equals to actual molecular weight. So S is the specific gravity of gas. And P is at standard is 14.7. R is 10.7 something. Temperature is 520. Do everything, then I get this equation. Tired. So we get this equation. And we can get this equation too if we express it differently. Okay, that's the derivation. Now you can calculate the in situ density. How dense is the gas? How many what does it mean? Pound per cubic foot. You can know that, right? Can you? How many pounds per cubic foot? One thing that we need to know is that one, compressibility factor. Compressibility factor comes from the chart. Tolani, did you restart it?
No.
You can do it now. Compressibility factor comes from the chart.